Hello everyone, my name is Ikram Bensaid and I am an associate professor at the University of Mostaganem. I am very pleased and honored to be speaking at the conference From Classical to Modern Analysis in memory of Professor José Carlos Petronillo. May he rest in peace. And before I start, I would like to thank the organizing committee for putting together this event and for giving me the opportunity to present my work, which is, by the way, a joint work with Bouzien Berrajo and Fernando León Saavedra. Today, I will be discussing the product of a particular class of bounded linear operators in Hilbert spaces, and which is the class of Posinormal operators. I got really interested in this topic because it is related to one of the most studied operators in operator theory, and which is the Cesaro operator. So recall that the Cesaro operator is defined in L2 as follows, and is represented by the matrix representation in the standard orthonormal basis of L2 by the matrix C. So the Cesaro operator plays a major role in both functional analysis and also in summability theory, where basically it transforms a sequence into its Cesaro means. So it is very helpful to analyze and to understand the convergence of sequences that do not converge traditionally. In operator theory, the Cesaro operator has been studied in different spaces and by many researchers. For instance, Hardy, Littlewood, and Polya established the boundedness of this operator in L2, and their proof was then improved by Brown, Helmos, and Shields. But probably the most known result about the Cesaro operator is the fact that it is a subnormal operator, and this was proved by Kriete and Truth. In 1994, Crawford really observed that the Cesaro operator satisfies the expression 1, where P is a positive operator on L2. Recall that bounded linear operator P is called positive if this inner product is positive, and in this case we write P is greater or equal than 0. Obviously every positive operator is self-adjoint. In fact, Rayleigh observed that there are many operators that satisfy the expression 2 and where P is a positive operator. For instance, some unilateral weighted shifts with non-zero weights, the P-Cesaro matrix in L2, and also some composition operators on the classical Hardy space that are induced by holomorphic self-maps of the unit disk. So it was very natural to Rayleigh to introduce the concept of posinormal operators. So throughout this presentation, we're going to say that a bounded linear operator T is posinormal if there exists a positive operator P such that the expression 3 is satisfied. And in this case, P will be called interrupter of T. Note that the interrupter might be not unique, alright? And it is clear from the definition that if T is normal, which means that T commutes with T star, then T is posinormal with interrupter the identity. Before discussing our new results, I'm going to first recall some known facts about square roots and absolute values of bounded linear operators. And then I will talk about some properties of posinormal operators. These properties were mainly found by Rayleigh. And then I will discuss some new results related to the product and absolute values of posinormal operators. Okay, so let's start with the first section. Assume that T is a bounded linear operator on a Hilbert space H. If you can find a bounded linear operator S such that S squared is equal to T, then S will be called a square root of T. For instance, the real matrices S1, S2, and S3 are all square roots of the identity matrix I. Another infinite dimensional example is the following. So if you consider the operator which is defined by the expression 6, then this operator is a square root of the Volterra operator V in the space L2. Observe that a bounded linear operator may have infinitely many square roots, as we just have seen with the identity matrix I2. Also, it is possible to find operators that have no square roots at all. For instance, the matrix M. And our intuition usually suggests that a square root is positive. However, it is not the case, because if you consider the matrix S, then S is a square root of T, but S is not positive. In fact, it is not even self-adjoint. However, if P is a positive operator, then P has a unique positive square root which we denote by the square root of P. So we use the symbol square root only when the operator P is positive. And here you have an example. Basically, the square root behaves in a good manner when it comes to the commutativity. For instance, if there exists a bounded linear operator S such that P commutes with S, then the square root of P also commutes with the operator S. Also, if we have two positive operators P1 and P2 with this order, then the square root of P1 is less or equal than the square root of P2. This is a particular case of the famous Lohner-Heinz inequality. And finally, if T is an arbitrary bounded linear operators, we know that T star T and T star are always positive operators, and so their square roots always exist. The square root allows us to define the absolute value of operators, which are sometimes called the modulus. The absolute value of a bounded linear operator is simply the square root of T star T. For instance, if the absolute value of the matrix M is given by the expression 9, and another example in infinite dimensional, which is the square root of the shift operator, is simply the identity, because we know that S is an isometry, so S star S is equal to the identity, and the square root of the positive operator identity is itself. For sure, the most important application of the absolute value is the polar decomposition of bounded linear operators. And we know that the polar decomposition is simply an extension of the polar decomposition of complex numbers, which is given by the expression 10. So the radius r will play the role of the absolute value of an operator, and the exponential e theta will play the role of the unitary operator. So, for instance, if T is a normal operator or an invertible operator, then it can be expressed as the expression 11 where U is unitary. However, if T is not normal and is not invertible, then in this case we are not sure of the existence of the unitary operator U. For instance, if you consider the shift operator S on L2, then S cannot have a polar decomposition of the type 11. For instance, if you assume that S has a polar decomposition of the type UP, where P is the absolute of S, then you will get that the shift operator is unitary, is U. But this is absurd because U is unitary and S is not. What we are sure about is that every bounded linear operator T on a Hilbert space H can be expressed by the expression 12, where V is a partial isometry, which means that V star V is equal to the identity on the orthogonal kernel of V. And here you have an example. And now we move on to the next section. Recall that a posinormal operator is an operator that satisfies the expression 14 and where P is called interrupter of T. If T is a non-zero posinormal operator, then its associated interrupter has a norm which is greater or equal than 1. And the proof is straightforward, using the boundedness of the operators T, P, and T star. Also, it is worth mentioning that the interrupter might be not unique. However, if we assume that T has dense range, then P is unique. For instance, if you assume that we have 2 interrupters for T, then the density of the range means that the kernel of T star is equal to the singleton 0, which means that T star is 1 to 1. So this is equal to 0 implies that P1 minus P2 multiplied by T is equal to 0. And which, again, using the fact that T has dense range, we get that P1 is exactly equal to P2. Surely, one of the most practical theorems for proving the posinormality of a bounded linear operator is the Douglas-Rayleigh theorem, which asserts that T is posinormal if one of the following conditions is satisfied. So, as a consequence, if lambda is equal to 1, then we get the definition of hypernormality, and so every hypernormal operator is posinormal. Also, every invertible operator is posinormal because the fourth condition is satisfied for S by taking S to be equal to this operator. And so, as you can observe, the class of posinormal operators includes too many operators, for instance, the normal operators, self-adjoint operators, and so on. So it includes a very large number, let's say, of operators. Note that the converse of these statements is not true, because if you consider the Cesare matrices of order P, then they are all posinormal, but they are not hypernormal for P which is greater than 1. Note that if P is equal to 1, then we get the non-Cesare matrix, which is at the same time posinormal and hypernormal. Another consequence of the Douglas-Rayleigh theorem is that the sum of posinormal operators need not be posinormal. In fact, not even their translations, as shows this counterexample. The next theorem asserts that if T is an invertible operator with a posinormal adjoint, then we can show that the inverse of T is posinormal with interrupter P minus 1. So, by assumption, T star is posinormal. So we have this. Since T is invertible, then its adjoint is also invertible. And so we can multiply by T minus 1 on the left and by the adjoint, by the inverse of the adjoint on the right. And so P is the product of bounded linear operators that are invertible. So it is itself invertible, and we can write this. Yeah, so T minus 1 is Posinormal with interrupter P minus 1, and it is easy to check that if P is a positive and inversible operator, then its inverse is also positive. So P minus 1 is positive, and we have the proof of this theorem. And now we move on to the last section and we present our new results related to the product of Posinormal operators. So it is a common question to ask whether the product of a certain class of operators remains in the same class. So under which conditions the product of posinormal operators remain posinormal? This question was mainly investigated by Kubrusley, Vieira, and Zani, Bourdon, Lee and Thompson, and so on. And basically, Kubrusley proved, and his co-authors for sure, proved that if T and S are two posinormal operators such that S star and T commute, then the product ST is posinormal. They also proved that if S is a normal operator and T is a posinormal operator such that T and S commute, then ST is posinormal. In the second part of this theorem, they used the famous Fuel theorem or Fuggledi theorem, which actually asserts that if a normal operator commutes with a bounded linear operator, then this operator also commutes with the adjoint of the normal operator. And here you have a photo of Ben's Fuel. May he rest in peace. As for our new results, we have proved that if T is a posinormal operator with interrupter P that intertwines S and S star, then the product ST is posinormal with the same interrupter of the posinormal operator P. This is the good thing about this theorem because it gives us an idea about the interrupter of the product. Also note that we didn't require S to be posinormal. And the proof is very simple. We have this is equal to this, which means that ST is posinormal, and we only use the fact that T is posinormal and the fact that T intertwines S and S star. As for the part 2 or part B of Kubrusley and Vieira and Zani theorem, we have proved that it is actually true even for hyponormal operators, not only the normal ones. So if S is a posinormal operator with interrupter P and T is hyponormal such that Ts star is equal to S star T, then ST is posinormal with the same interrupter of the posinormal operator P. So we know that if that the operators T, T star, and T star T are positive, and since T is hyponormal, we have this. So we can multiply by S on the left and S star on the right, and we have this. And this is simply the product of ST with its adjoint. And now if we focus on this operator which is here, then since we have assumed that Ts star is equal to S star T, then this second, these two operators are equal to S star T, but again here S is posinormal, so we can write it in this way. So basically we have the product of ST with its adjoint is less or equal than the product of the adjoint of ST by P and ST itself, which means that the product is also posinormal. And now we move on to the last section of this presentation. We know that it is possible to characterize self-adjoint positive and normal operators using the absolute value. Is it possible to have a similar result for posinormal operators? Where the answer is yes, and we have proved that T is posinormal with interrupter P if and only if the absolute value of the adjoint of T is equal to the absolute value of the square root of P multiplied by T. Now, since P is positive, we are sure of the existence of the square root of P. Also, since it is positive, the square root is always self-adjoint, and so it is quite easy to prove that T star Pt is actually equal to the absolute value of the square root of P multiplied by T squared, and also that Tt star is simply the absolute value of T star squared. So we have an equivalence between these two, and the proof is finished. As an application of this theorem, we have the following result. If T is an invertible operator, then we can find a unitary operator U and a positive operator P such that the adjoint of T is equal to this operator. In fact, since T is invertible, its adjoint is also invertible. And by the polar decomposition of invertible operators, we know that we can express the adjoint of T as follows. And according to the previous theorem, we may write the absolute value of T star in the following way, because T star is invertible, and according to Douglas' theorem, it is also posinormal. So the previous theorem applies. And this actually ends the proof. Finally, we have this Cauchy-Schwarz inequality for posinormal operators. Namely, if T is posinormal, then there exists a non-negative scalar alpha such that this inequality is satisfied. So the proof is based on the Douglas theorem, the Douglas-Rayleigh theorem, which asserts that there exists a positive lambda such that Tt star is less or equal than lambda squared T star T. And this can be simply written in terms of the absolute value in this way. Now we can use the famous Loner-Heinz inequality, which gives us the expression 15. And then, applying it to the known Feruta's inequality, we obtain this, and we can take the square root to obtain the desired result. As a future work, we aim to study, we plan actually to study the posinormality of the sum, and also its generalization or its extension, which is the supraposinormality. So under which conditions the sum of two posinormal operators or of two supraposinormal operators is still posinormal and or supraposinormal. This doesn't seem to be an easy question. It's not a trivial question, but it is worth to investigate. Also, we plan to study the powers of supraposinormal operators, and finally, what is the absolute value of the Cesaro operator, and what is, for instance, the absolute value of composition operators that are induced by holomorphic self-maps of the unit disk in the classical Hardy space H2. So it is good to know if these were possible to calculate. So this is the end of my presentation. Thank you very much for your attention, and here you have some references. Thank you.